Good morning, and it's my great pleasure to give a talk about my research. I'm Honglak. I'm assistant professor in computer science and engineering, and today I'm going to talk about learning and selecting features jointly with pointwise gated Boltzmann machine. This is a joint work with my students, Ki-hyuk Son, Kwan-yu Jo, and Chan-Soo Lee, and this is going to be presented at ICML this year. So we are living in the world of big data. So we have just all kinds of different data modalities, such as image, video, speech, music, text, and so on. And also lots of healthcare data in all kinds of different modalities. Also, we have lots of multimodal sensors. Could be some infrared or some range sensors and so on. Okay? And machine learning and data mining is a crucial enabling technology to actually learn from these patterns and be able to mine patterns and predict for some tasks. For machine learning, it's actually one of the very important problems to actually figure out what the good feature representations are, because they are very crucial in achieving good performance. But in practice, these are actually crafted by hands, by experts. So in today's talk, I will focus on how to learn features instead of handcrafting these features so that we can generalize to different type of data easily. So here's a cartoon diagram of how computer perception or pattern recognition is done. So we are typically given some raw data, which is very high dimension and complex. And in order to deal with this, we need to come up with some kind of feature representation. This is often done by hand tuning or handcrafting. And then we just put this feature representation into learning algorithm. So for example, for image recognition, we take some edges. So we do some edge detection and do some histogramming and additional post-processing and get some low-level visual features and then put into learning algorithm. Similarly, for audio classification, we take some short-term Fourier transformation and then compute the spectrum and then do some additional post-processing and put into learning algorithm to predict some task. The problem of these type of features are that first it requires domain expert knowledge, and also it's time-consuming, and it's actually quite painful to tweak these parameters to find out good features. And also it doesn't generalize, meaning that good video, good image or video feature will not generalize to good audio features. So recently, feature learning, or so-called representation learning, has been one of the most emerging field in machine learning. And the main idea here is that we can actually learn some statistical structure or correlations even from unlabeled data, and possibly with some labeled data. And as another key idea, we can actually try to learn abstraction. So we can learn multiple levels of abstraction so that we can find more high-level concepts or features. And also, these type of algorithms can be also combined with supervision. So we can do supervised or semi-supervised learning. So for image, we can think about some task where we are given a bunch of face images and try to learn some hierarchical representation that can decompose into parts and full objects, such as starting from pixels, we learn maybe edge detectors, and then it learns some higher level concepts, such as object parts, and combine these object parts to learn full objects. And this type of hierarchical features can be very helpful in filling in the representation gap in machine learning, because most of the state-of-the-art machine learning features operate in the very low-level feature regime, such as edges. So this type of algorithm can not only be applied to images, but also can be applicable to audio to give some dictionary or some high-level dictionary elements. Or it could be applied to text, and it can give some kind of topic models. And also it can be applied to medical or robotics data. So in today's talk, I will focus on how we can combine feature learning and feature selection. So this is a more challenging problem, because when we want to deal with data that has highly irrelevant patterns, then we need to be able to not just learn features, but also figure out what are the important patterns so that it can focus on these important patterns. So for this, I will first talk about some backgrounds and then talk about our model and experimental results and finish. So let me start with some background materials. So here are some examples of how we learn from images. So suppose that we take some small 10 by 10 image pixel patches from natural images on the left-hand side. And then we can try to represent these image patches as some kind of combination of basis vectors. So X is a data vector, B's are the basis vectors, AJ's are the coefficients. And with some additional constraints such as imposing sparsity, we can actually learn some features. On the right-hand side, I'm showing some set of basis vectors. So the meaning of this learning is as follows. So given some new test example, we can try to decompose into some sparse combination of these bases. So for example, we can pick some edges and then combine this together. And here, this image patch, which is originally 10 by 10 pixel patch, is represented by some coefficients of few basis vectors. And we can use these coefficients as features. And by doing so, we can transition from pixel level representation to some kind of edge detector based representation. And we can get some higher level abstraction. Okay? And we can do this type of learning recursively. So we can, assuming that we can learn this type of edge detector in the first layer, where in this picture I'm showing blue circles as the actual original data, which could be pixel level patch. And the white circles represent the coefficient. And the link between the white circle and the blue circle represent the weight or connection between these two. That can be visualized as some kind of edge detector like this. But we can do this type of learning in higher layer that can potentially learn this conjunction or some composition of these low-level features. So I'm going to just briefly talk about one of the most important algorithms for doing this type of learning. So this is called restricted Boltzmann machine. And this is undirected bipartite graphical model. So you can just think about it as a Markov random, one specific form of Markov random field that has binary observations and also binary hidden latent variables. So this V or binary observation represents the data that you get, and the H represents some latent variable that are used to represent this original data. And here, we can easily extend the model so that it can take real value data or other type of data as well. But I'm going to just talk about specific case of using binary input values. So we can represent the probability as some typical standard energy-based representation for undirected graphical model. And this energy function is represented as some interaction between the input Vi and hidden node Hj and their connection Wij. So let me just explain some slightly more detail of how we can interpret this energy function. So it turns out that we can just rewrite this energy function in this form. And I'm going to give you a quick animation of what this means. So if you look at the first term, we have H1 W1 transpose V, where this W1 represent the vector that are red colored, arrows that are red colored, which represents some kind of filter or basis vector corresponding to H1. So what this means is that you do some kind of template matching. So you compare whether W1 matches V, and if it matches well, it will have a high value. And that induces high probability of H1 being 1. Otherwise, if W1 doesn't match V, and then H1 will be 0 with high probability. So you can do this simple arithmetic for different type of hidden units. And basically, you can see that different hidden units will have different filter, and it'll basically compare whether that filter matches the input data and determine whether you want to turn it on or turn it off with some probability. So this is what the restricted Boltzmann machine is about. And this is just a graphical model with this binary latent variable, so you can do some standard maximum likelihood training. And here, I'm going to just briefly talk about how to do inference. So inference means, for example, given the visible data, how these posterior probabilities of HJs are. That's the, for example, posterior inference for this RBM. It turns out that this type of probability can be very simply represented as some kind of independent product of these functions. And actually, we can just rewrite things, and it just turns out to be some sigmoid function of Wj transpose V plus Bj. So roughly speaking, sigmoid function is some kind of nonlinear function that kind of squashes your input to some value between 0 and 1. So that gives you some probability. And basically, the more Wj matches V, it will have higher probability of being activated. So we can use this type of probability as feature, which means that given the data, we can learn this model and use this type of posterior of hidden units as some kind of alternative representation for maybe classification or other tasks. So we can apply this type of algorithm to, for example, handwritten digits, where here the small digits shows individual training example. And we can learn this model, and it will learn some kind of basis vector that look like a pen stroke. So what this means is that the model has learned to decompose the original training data into this combination of this small number of pen strokes, which is a kind of very plausible outcome. So I'm going to talk about some new models that can address some limitation of this work. So one motivating problem is a problem learning from scratch. Suppose that you just learn from the world from nothing, actually. So if you don't have any good knowledge about the world, what can you do? So we know that there are some good algorithms, such as unsupervised feature learning that I just talked about. So these algorithms are very powerful in learning useful representation from unlabeled data. However, one big limitation is that actually not all patterns are equally important. And also in real world, where there are lots of distraction or irrelevant patterns, learning will quickly stagnate because the learning algorithm doesn't know which pattern is important, which pattern is not. So we can think about alternative approach, for example, feature selection. So feature selection has been a very powerful workhorse in machine learning. Basically, they can select some subset of features from huge number of features that may contain irrelevant features. The limitation is that this feature selection algorithm assumes the existence of useful feature. So actually, if you just start from nothing, basically there's not much you can do because feature selection assumes that there exists some good features. So in this work, we try to unify these two frameworks for feature learning and feature selection that can perform feature selection in higher levels and also do some feature selection in a dynamic way in lower levels. And also, of course, it will learn some features as well. So here's some example of what this algorithm is doing. So suppose that we are given data like this, where our problem is doing some digit recognition, but it contains lots of noise or irrelevant patterns. So the problem has become much more challenging, and also, the unsupervised learning will basically try to learn not only some meaningful pattern that relates to digit recognition, but also some kind of background patterns as well. So in our algorithm, what we try to do is to learn some distinct set of features. For example, so-called features for foreground or features for background. So here, the feature for foreground means features that are relevant to the task. So it can be any kind of task. So it learns some kind of digit pen stroke-like features for the foreground. And it learns also some kind of random background features. And it'll try to figure out how to combine these features together to generate the data. In order to do this, we need some kind of binary masking variable. Here, where this mask value of 1 means that you want to generate the pixel value from the left-hand side. when the mask value is 0, then it means that the model will generate the pixel value from this right-hand side background features. So we can connect this model using some undirected connections. And the main intuition is that it has learned some kind of set of important features and unimportant features and tried to explain how to interpret this data as some combination of foreground and combination of backgrounds. Okay. So, so this is a more simpler diagram that are just showing just 2 pixels and the switching variable for these 2 pixels. So this switching variable can take 0 or 1, and when it takes the value 1, then it'll you just multiply this V1 and Z1, and then you can generate from this group 1 hidden node. If the switch units are 0, then you generate this input data from the right-hand side group 2 hidden nodes. And you can also extend this model to connect the label units to the foreground hidden units. The rationale here is that the unimportant features that are learned from this model shouldn't affect the labels. So by doing so, the model can actually perform feature selection in these hidden layers. But also, it turns out that you can do feature selection in the original visible nodes, which I'm going to show a little bit later. So if you apply this, so here's some math, but it's not that important, so I'll just skip this. So if we apply this to this type of digits that have some fairly distracting background, here are some results, and these are the algorithm that we compare as a baseline. So we compare to restricted Boltzmann machine and some other extensions of restricted Boltzmann machines, and also restricted Boltzmann machine combined with feature selection as a 2-step process. It turns out that feature selection just combined with this feature learning, just as a two-step process, doesn't give as much improvement as we expect. However, when we compare our methods, we actually achieve consistently better results. And also, it turns out that the supervised version of our algorithm performs slightly better than unsupervised version of our algorithm. And we can also compare to some other deep learning methods, such as deep belief network or contractive autoencoders. And again, we achieve significantly better improvement, better classification accuracy. And here the rationale is that if you just learn some deep network from this type of distracting data, then it can learn lots of unimportant patterns. So if you have lots of unimportant patterns, and if you try to learn additional correlation out of these lots of unimportant pattern, then the learning can be easily distracted. So that's possibly why this deep learning algorithm, standard deep learning algorithm, doesn't work as well. And I'm going to briefly talk about how to learn these type of features from more challenging data, such as high-resolution images. So the question is, given some cluttered background images, how can you find relevant foreground features? And this is a problem of weakly supervised learning, where we are not provided actual bounding boxes, but just provided just class labels. So our strategy is to learn features in an unsupervised way, and then figure out which features are useful in discriminating the classes. And then we will jointly train this unified model that can perform both feature learning and feature selection. So before I move on, here's some kind of background work that I have done that can learn some hierarchical decomposition from images. So given this type of images, the algorithm will try to learn some edge detectors from unsupervised learning. And it can be visualized as some kind of activation that correspond to these filters. So horizontal filter will give you activations of hidden units when the horizontal contrasts are prominent, and similarly for vertical filters, diagonal filters, and so on. And you can learn this hierarchical representation on top of this. So you can learn another layer that will learn additional correlation between these first layer outputs, and you can learn some object parts. And this right-hand side shows where these object parts are activated. And you can do this recursively for higher level features. The problem of this type of approach, although it works really well, the problem is that if you have really distracting patterns, then the algorithm will just try to learn all these things together. So what we propose in this new work is actually some extension of this, where in learning the second layer, we kind of tease into two components, where the one component is some kind of task-relevant patterns. The other component is task-irrelevant patterns. So if you provide class labels such as faces or non-faces, the algorithm will figure out some class-specific features and non-class-specific features. So here are some examples of these bases, and here are the actual localization result. Because the model, if you go back to this result picture, the model can basically figure out where the original input pixels are that correspond to the task-relevant pattern or not. So you can do some localization like this, and you can do also similar task for car versus non-car, and it learns this distinct set of features, and it can do some localization like this. And you can do some similar style learning for generic foreground object versus non-foreground objects. And it learns some distinct set of features where the foreground feature look like some slightly more artificial pattern that may be more relevant to objects, whereas the background feature learns some more generic patterns. And we can do also similar style of localization. And the one useful thing of this localization is that we can actually focus on the data and only look at this interesting part. That actually helps us to do better classification on image categories. So this result shows that by this type of localization through this joint feature learning and feature selection, we can actually achieve significant improvement from the current state of the art. So in this talk, I have presented some new model that can perform joint feature learning and feature selection in a unified framework. This type of model can learn useful features, but also can dynamically focus on relevant part of the data, even when you don't have good features to begin with. And the algorithm can learn good useful features from significant amount of irrelevant or distracting patterns. And it can also be applied to weakly supervised learning. And this, I'm hoping that this type of learning can be also applied to other domains, such as speech or text and so on. So thank you very much for your attention, and I'll be happy to answer any questions. Thank you.